What's going on, everybody? This is Mr. Diamond here with your Chapter 8. I don't know if you can hear me doing the air quotes, but Chapter 8. We're going to call this the Chemistry Speed Round. And this is the last few things that I feel like is important for me to teach you before you go. Since we don't have nearly enough time to cover a full chapter digitally, it would probably take us 3 to 5 weeks to cover a full chapter digitally, even though it would only take us about 3 weeks in person. So I just want to focus on a couple of things that I think are very important, especially those of you who are planning on taking other chemistry classes in the future, whether they're mine or if they're in college. So the topics are concentrations, specifically molarity, dilutions, acids and bases, and then pH and pOH. Each one of these will kind of be its own day. And then I'll post some example problems. I'll actually be doing them in the same video. And then there'll be 1 or 2 days worth of problems related to them that are pretty straightforward. And then your final will have a couple of questions based on these things as well. Your final is going to be only a little bit longer than the test that you guys took last week. Getting a drink to maintain that proper hydration, which you should be too. So, first section we're going to talk about is concentrations. And we're going to start with some definitions that I believe you guys should be somewhat familiar with. I think we talked about solution in class before, solutions. Solutions are homogeneous mixtures of 2 or more substances in a single phase. Now, usually this phase is talking about states of matter. I can't think of an example of a solution that has things in separate states of matter, because by being in separate states of matter, it would no longer be homogeneous. You could kind of tell distinct parts of it. Remember, homo as a prefix means same, so homogeneous mixtures should look the same. Like when you have a jug of Kool-Aid, even though it's a mixture, it is water and Kool-Aid powder, it looks like it's the same substance throughout. So that's a homogeneous mixture. The opposite of that would be a heterogeneous mixture. Heterogeneous would just be something that looks different throughout, like muddy water, or hot cocoa with marshmallows floating on top, or something like that. Solutes are the substance that is dissolved in a solution, or it's the thing that there is less of present. The reason for this is because notice it doesn't say it has to be a liquid. They just have to be in the same state of matter. The air around us right now, I'm waving my hand in front of my face to, the air that's floating around all of us right now, is actually a solution. It is a homogeneous mixture because you can't tell that it's made out of any multiple parts, but it is a mixture. There's tons of gases. There's water vapor, there's nitrogen, there's oxygen, there's carbon dioxide, there's carbon monoxide. There's all sorts of gases, but you can't really see them. You can't tell any difference. It's all clear to us. So that is still a homogeneous mixture. The solute, instead of it being dissolved, would just be the things that there are less of present. Solvent is the thing there is more of present, or that does the dissolving. So in the case of air that's around us, the thing that there is the most of present is nitrogen. Nitrogen makes up a major portion of the atmosphere around us. So nitrogen would actually be the solvent for normal air, atmospheric air. And water vapor, oxygen, carbon dioxide, carbon monoxide, all of those things would be the solute. Even though, again, they're not dissolved, and nitrogen doesn't dissolve them, it's just in certain cases we can't really think of something as dissolving or being dissolved. Now, for concentration, our actual thing that we're going to be talking and focusing on for this section, that is the measure of the amount of solute in a given amount of solvent. And generally speaking, it's just a way of describing how much stuff is dissolved in some other stuff. Something that has a lot of substance dissolved in it, we call that concentrated. If you think of like orange juice from concentrate, or concentrated bleach or hydrochloric acid or something like that, that means that there is a lot of that substance dissolved in the solvent. And if it's a small amount, we call that dilute. You may have heard that it's, a very dilute amount of poison, or you've diluted the tea or diluted the drink with water, or whatever you could be talking about. But dilute means less of something, or concentrated means more. Notice that I never put a number to that. Like, concentrated is not like if more than 50% of the mass of this, like it's not something like that. It's just a qualitative term. For certain acids, concentrated might mean a very, very, very small amount. Whereas if you had that amount of orange juice inside of that liquid, you would probably call that very dilute. Like having 0.0001 moles of orange juice in a cup of water is not going to do much. But having 0.0001 moles into a cup of water of acid is probably going to be a dangerous pH that could really hurt you if you're not careful with it. So these terms are qualitative. They don't have actual numbers associated with them. Now, there are a ton of ways to represent concentrations, and we would have, if we had this as a full chapter, gone through all of these at least a little bit. If you take advanced chemistry, we will go through these. There's percent by mass, percent by volume, mass per volume, molarity, molality, and mole fraction. Now, these three are the ones that I assume seem the most weird to you, and they are the ones that we will, in fact, be using the most in the class, or would be, at least, if we were still going by it. But we're going to focus on this one right here, molarity. Molarity is a measure of how many moles of solute, so moles of solute is on top, are contained within 1 liter of total solution. So you take your moles of solute, divide by your liters of solution, and it is represented with a capital M. Now you might be thinking, oh, is that why, well, wait, if we couldn't use like capital M to represent moles, why couldn't we use lowercase m? And I mentioned that it actually stood for meters, but lowercase m is also molality. So molarity is big M, molality is little m, and then moles you have to represent as MOLs. I have no idea why they decided to do it that way. That seems, weird to me, but I wasn't at the meeting where they decided that. So to find moles of solute, you'll often need to do a stoichiometric conversion. So you'll, convert your grams to moles and then put moles over liters. The only other trick to keep in mind is that the volume on the bottom is the volume of the whole solution, the solute plus the solvent, while the top is only solute. That'll only really come up at super tricky problems that I'm probably not going to have enough time to give you. The only other tip that I don't actually know if I put in here, but just in case, I want to make sure that you've heard at least from somewhere. Water, it has a density of 1 gram per milliliter, which means if you know grams of water, like if you're given 50 grams of water, that's the same thing as getting 50 milliliters of water. Remember, it has to be converted to liters, but I could give you 2 grams numbers and ask for molarity if I gave you either the density of the solvent or if you know that the solvent is water, because if the solvent is water, every gram corresponds to a milliliter, every kilogram corresponds to a liter. So we're going to do 2 examples. I'm going to switch over to the hand cam in a second. You have 3.50 liters of water that contains 90.0 grams of sodium chloride dissolved in it. Find the molarity of the solution. And then example 2 is how many grams are present in 500 milliliters of a 1.5 molar sulfuric acid. I've been working with a bunch of acids in advanced chemistry. So H2SO4, which is sulfuric acid. Now, also just note, this is also important for advanced chemistry and other chemistry classes. These brackets represent molarity values. So if you ever see these brackets, and this will actually also become really important in the next section we'll talk about, but brackets just represent molarities. So I'm going to go ahead and switch over to hand cam. Okay, hopefully we're switched over. I'm going to switch over on my computer screen to bring on my periodic table so we can work these out real quick. There we go. Okay, so our first problem is we have 3.50 liters of water that has 90.0 grams of NaCl, that's sodium chloride. What is molarity? Okay, so looking, and I'll write the second one just so I don't have to keep clicking back and forth between them. Our second question is how many grams of H2SO4, because it says how many grams are present in 500 milliliters of that. I guess it was kind of vague in the problem, but you're looking for grams of H2SO4 are present in a 500 milliliter of 1.5 molar H2SO4 solution. Okay, now I can prevent myself from having to click back and forth. So for question number 1, molarity, as we saw in that equation earlier, is moles of solute over liters of solution. So our moles of solute, we don't have that, but we have our liters of solution. So we're going to go ahead and take our 90.0 grams of NaCl. We know that because it gave us this value in grams, and I'm not going to be a jerk and I'm not going to try to trick you, this value that was given in grams must be your solute because I gave you a liters of the other thing. Now, in later problems, I might give you 2 grams numbers, but if I give you a grams and a liters, I'm not trying to trick you. The grams is the thing that's the solute. The liters is the thing that is the solvent. But we're going to have to convert our grams to moles. So I'm going to go ahead and get my calculator. Na has a mass of 22.9. 9, and then plus Cl is 35.45. I've done enough of these now that I actually have Cl memorized. So we've got 58.44 grams of NaCl is in 1 mole of NaCl. Now you might think, okay, well, where do we go now? Do we convert that to H2SO4? Do we and no, well, I don't know why we do that. That's a separate problem. But we don't have to convert it into anything else. We just need to get it into moles. So I'm going to go ahead and take my 90. I'm going to divide it by 58.44. And I get 1.54, and then I have 0, 0, so I'm just going to stick it with 1.54 moles. And then, if I don't hit my paper out of the way, molarity is going to be equal to 1.54 moles, MOL again is the abbreviation for it, of NaCl divided by 3.50 liters of solution. Means that we will have a molarity 1.54 divided by 3.5 of 0.44. Now just to double check, 90.0 and 3.50, so we're actually going to have to add a 0 to the end of it. So 0.440 equals the bracket concentration of NaCl, or the other way you could write it is 0.440 big M molar of NaCl. Either one of those methods of writing it would be acceptable. So 0.440 molar of NaCl. And that is how you pronounce when it's molarity. You say it is molar, which is weird because molars are, teeth. But whatever. Again, I wasn't at the decision or the council where they made that decision. So for number 2... this time we still know that molarity equals grams of solute, moles of solute over liters of solution. If you like, you could in theory do one of those little pyramid things. Those do actually work for this. So it would be, I believe, molarity, mole solute, and then liters of solution. Man. So you could do this as a little one of these like pyramids, like the density pyramid or whatever. Molarity would be here, moles of solute would be here, and then liters of solution would be here. In this case, we have 1.50 molar, 1.5, there's just 1.5 molar equals, and we have moles of solute as our unknown, over, we have 0.500 liters. Now, you might be wondering, well, that's not the number it gave you in the problem, but it gave me milliliters, and remember that we can do 500 milliliters. There are 1,000 milliliters in 1 liter, which gives us 0.500 liters. So I just moved my decimal. You don't actually have to show this conversion, but you do need to make sure that it is in liters before you do it. So now we can rearrange. So moles of solute is just going to be equal to 1.5. We'll multiply that to the other side times 0.5, which you might be able to do in your head just in case. 1.5 times 0.5, you get 0.75. And this is moles of H2SO4. And now I'm going to take this number, and I'm going to do it directly. I know some of you might want to go down here, but I'm going to be doing a whole lot of problems on this today. I'm just going to power through probably all of the notes that you guys are getting for the rest of the year. So I'm trying to be as paper efficient as possible. So for H2SO4, you got 2 hydrogens plus a sulfur, which is 32.06 plus, so that's H2S, and then 4 times 16. So we got 98.08. So 98.08 grams of H2S. Oop, flip that. Because we have moles on bottom, or moles on top, we need to put moles on bottom. So 1 mole is 98.08 grams of H2SO4. So moles of H2SO4 will cancel. We'll be left with 0.75 times our answer right there. And we will get 73.56 grams of H2SO4. Or, I guess technically, because of sig figs and getting bad about that today, apparently. We have 1.5 and we have 500. 500 does not actually have a decimal, so it actually would just be 0.5. But I intended there to be 500 points. So we'll take it to 2 sig figs. So we'll call it 74 grams of H2SO4. Although you've probably realized at this point that the digital stuff, I don't really check the sig figs too much anyway. It's just not really worth the time it takes to figure that out. Okay, so and what this is saying again is this is how many grams if you have a 500 milliliters or 0.5 liters of a 1.5 molar solution of sulfuric acid. That solution contains approximately 74 grams of H2SO4. Technically a little bit less, but sig figs tell us it would be 74 grams of sulfuric acid. All right, I hope those examples made sense to you. The problems you're going to end up having to do in class are not actually going to be, or online, are not actually going to be too much worse than this. If you have any questions, feel free to send me an email. I could try to help you work it out or help understand it better. There's also probably plenty of videos doing molarity problems online. Hope you have a great rest of your day. Hope you have a great week, and I hope to see or hear from you soon.